All right, so welcome everyone. I'd like to get this meeting started. First of all, I'd like to introduce our committees here for Tristan Goers. So we have, so I'm Kaisha Wang, I'm the committee chair, and I'm also from the Department of Geomatics. And we also have Kenrick Mock, who is our current interim dean of the College of Engineering. And we have Tom Raven, who is a professor of the civil engineering. So for today, let me know if the procedure is not correct. So my plan is we have a presentation first, and then come to the question and answer session. So after that one, I'll ask Tristan to step out of the Zoom meeting room, and then as a committee members, we have internal discussion, make a decision. Then we'll invite Tristan to join back for the decision. So after that one, that's kind of wrap up the defense of the thesis. Is there any questions or suggestions, Tom and Kenrick? If I miss any steps, please feel free to let me know. This is my first time doing it.
Nope, I think
you're doing great.
Good to go.
All right. Okay. So let's get started now. So Tristan, a little bit background about Tristan Goers. He actually graduated from our geomatics Bachelor of Science degree in 2018. And after that, he got a chance to work with the ADAC Center as a research assistant for 2 years. So that's a great opportunity that also helped him to work on the master degree with me for the interdisciplinary studies in the data science. And without further ado, so Tristan, go ahead. The floor is yours.
All right. Thank you, Dr. Wang. So hello, my name is Tristan Goers. I am a Master of Science candidate in the interdisciplinary studies in data science. My thesis presentation is on deep learning for damage assessment after natural disasters. Here's my outline for my presentation. I would first like to discuss problems and motivations of my research. Then I will discuss my proposed approach. Then my experimental study using Port-au-Prince, Haiti as a study site. And then finally, I will discuss my conclusions and future work. The problems and motivations. In recent decades, we have witnessed the ever-growing occurrence of natural disasters. According to the United States Geological Survey, between the years 2000 and 2012, there have been 807 earthquakes above a 5.0 magnitude. There have been nearly 24,000 earthquakes, with an estimated 790,000 deaths. The 2010 Haitian earthquake, for example, killed between 220 and 250,000 people, while also collapsing and destroying 250,000 residential and 30,000 commercial buildings. It is vital that emergency response personnel get informed in a timely manner as to where and how severe building damage has occurred. Remote sensing is a powerful tool in detecting and classifying damaged buildings. Two general challenges in the field of image classification for disaster response exist, including the availability of data resources for analysis and deriving accurate and actionable information in near real time. Aerial imagery has extensively been used, but image swath covers a small area, while flight operations also may be costly. The satellite's major bottleneck is its location, as it may take time to get to a disaster area. In a nadir view of a building, looking straight down at it, mostly only the rooftop can be viewed. If the satellite is far away from a disaster site, it may give highly oblique images, giving rise to additional data issues. During a limited time frame scenario, a compromise must be reached among response time, analysis depth, and mapping accuracy. Several works attempt to address challenges from a fundamental pixel-based approach to the more advanced deep learning methods. Pixel-based approaches rely on spectral characteristics of surface features of images. Pixels are also exploited without much consideration to their spatial context. One type of classification is supervised. It's where a human must select sample sites on an image that is representative of known human-defined classes. The spectral properties of each pixel are compared to the human classes and then grouped. Another type is unsupervised. So pixels are divided into several classes based on the pixel's natural grouping. This is accomplished without any training data or prior knowledge of the study area. A major issue with this method is the salt and pepper effect of pixel classification. Here in this image, we can see in the field is supposed to be classified as surface vegetation. However, we can see the salt and pepper effect of classification of built area in purple and trees and shrubs in dark green. The object-based approach does not operate on individual pixels, but instead on homogeneous and spatially contiguous groups of pixels. It's superior when compared to a pixel-based approach when using image segmentation. That is the process of partitioning an image into multiple segments in order to simplify the representation of sets of pixels into something more meaningful and easier to analyze. While using many characteristics of the objects, such as context, texture, and pixel spectra, object classification is done using an algorithm like the common k-nearest neighbor algorithm. In the image to the right, we see there are lines representing image segmentation. You can see how the lines kind of follow features of the map. So machine learning is a subdivision of artificial intelligence and deals with the construction of algorithms to learn from data. Images with high spatial resolution require a more versatile and robust classification solution. In unsupervised classification, the classifier attempts to find hidden patterns using similarities in the data set. In supervised classification, a mathematical model is trained to map input records into a known class. The support vector machine is one type of machine learning algorithm. It's originally a binary classifier. The optimal hyperplane discriminates data into classes. A linear SVM assumes the feature data is linearly separable. In practice, however, data points of different classes often overlap, thus kernel functions are introduced. Here we can see a depiction of the support vector machine. In image A, you can see that there are many different hyperplanes that can discriminate between the two classes. In image B shows the optimal hyperplane in the middle with two support vectors flanking it with a defined margin. Random forest is another common machine learning algorithm in damage detection. It's made up of many decision trees. The random forest train many decision trees independently using random subsets of training data. Using only subset of training data and a subset of variables, each tree will be less accurate. However, it will also be less correlated, making the whole random forest more reliable. One advantage of this is that it reduces the danger of overfitting. A single record can be analyzed through multiple decision trees, giving multiple classifications. A simple majority vote in all of the decision trees is taken to find the final class. Here, a record starts at the root node, traveling through decision nodes, and finally ending at a leaf. At each node, a decision is made based on the variables in each record or on a predefined set of splitting rules. Once complete, the decision tree will assign a single label to the record, thus classifying it. Image segmentation and pixel-based methods are challenging in a dense city such as Port-au-Prince, Haiti. It would be difficult in an object-based method of classification to apply segmentation effectively to create building objects. The pixel-based approaches, salt and pepper effect would be nearly too much to overcome in a dense city with homogeneous buildings. Some machine learning models require a lot of training data, and extracting and labeling building footprints is a time-consuming task. When trying to get building damage information to emergency response personnel, a fast turnaround on classification is very important. Models are often only suitable for one type of building and are disaster specific. Models that are trained on different types of infrastructure with different parameters. A model that is trained in Port-au-Prince after a earthquake may not be suitable for detecting damaged buildings in New Orleans after a hurricane and flood. Now I want to talk a bit about my proposed approach. The artificial neural network is a machine model that is inspired by the structure of the neural networks in the brain. The network consists of many connected neurons, each of which produces a series of activations. These neurons are activated through sensors perceiving the environment through weighted connections from the previously activated neuron. The feed-forward neural network is the simplest artificial neural network there is. Information from the input node moves through the hidden layers and then out the output nodes. There are no loops in this type of network, hence feed-forward. A subclass of feed-forward network is called the Convolutional Neural Network, or CNN. CNNs are the most representational deep learning model for image recognition, as CNNs were specifically built for image recognition. CNNs were specifically designed for computer vision and image classification tasks. CNNs also automatically detect important image features without any human supervision. Shared weights decrease the model's parameters, and a lot of training data is required. As a theoretical example of weight sharing, a one-layered CNN with 10 filters of size 5 by 5 will be given a convolutional neural network 250 weight parameters. Let's say the model has 10 biases, so the total number of parameters would be 260. In contrast to that, using an artificial neural network with 250 neurons will have 19,600 weight parameters and one bias parameter, for example. If using an image of 28 by 28 like this, so this image right here would have 19,601 parameters. CNNs also have the potential to encode spectral and spatial information into the classification automatically. Functions defined by weights and biases are optimized. With more layers stacked, more complex features can be learned. Overall, the CNN architecture includes an input module, convolutional backbone module, and a classifying module. This modular composition makes CNN approach highly adaptable for different tasks. Sequentially, CNNs repeat convolutions, activations, and poolings. It follows a hierarchical structure of a natural signature and mimics the behavior of the visual cortex of living mammals. For humans, visual information is passed from one cortical area to another, each more specialized than the previous. The neurons in each specific area only respond to specific actions. For example, primary visual cortex preserves the spatial location of visual information such as edges or lines. The secondary visual cortex collects spatial frequency, size, color, and shape. The third visual cortex processes motion and gives a complete visual representation. There are a number of other steps, but you kind of get the point. The visual cortex acts as layers of the CNN. Edge detection, like in primary visual cortex, can be detected by CNN kernels. Max pooling layers can detect where objects are located. Humans can recognize the face, even if it's inverted, rotated, or flipped. Using data augmentation, we can convert a single image into many types of images to train the CNN. Degradation occurs when a model gets deeper, and it becomes more difficult for layers to propagate information from the shallower layers, causing information loss. A residual network, or ResNet, is constructed from residual building blocks to address the degradation problem. Instead of skipping a few stacked network layers and fitting the underlying mapping, this model fits the residual mapping. The ResNet is one of the most promising convolutional backbones. Identity mappings are important parts of the residual learning block. The core idea is to learn the residual function. This is achieved by attaching the identity skip connection or shortcut to the ResNet model. The shortcut connections do not introduce extra parameters to the equation, nor do they introduce additional computational complexity. Looking at this figure, we can see a model of a ResNet building block. Let's use h of x to represent output mapping function. The output mapping function equals the residual function f of x, shown here, plus the identity of the previous input x, shown here, using these skip connections. So I will use a 152-layer ResNet model in my approach. In this approach, I will use a 128 by 128 by 3 red, green, blue image, processed into a 7 by 7 convolutional layer, shown here in the bottom image, which feeds into a 3 by 3 max pooling layer, and then into a 3-layer residual building block in a bottleneck design. First a 1 by 1 convolution, then a 3 by 3, and then a 1 by 1. This reduces the number of parameters while not degrading performance of the model as much. As discussed, my pre-trained model will be the 152-layer residual network model, which will be used to classify damaged and non-damaged buildings. Next, I will discuss transfer learning theory and model fine-tuning. Training deep models from scratch typically requires a data set of sufficient size and training time, typically weeks or months. The ResNet 152 model used in my work was pre-trained on 1.2 million images of the ImageNet database. Generic image descriptors can be extracted from unrelated data set and applied to different image classification tasks via transfer learning. So a model that's trained on a bunch of nature images can be transferred into a model that's going to be training on damaged buildings, because the model learns generic image descriptors. In transfer learning, the base model is trained on base data set and task. These learned features are then transferred to a second target network to be trained on the target data set and task. The shallow part of the model tends to learn filters that correspond to more general image features such as edges and corners. In the image here, we can see that the source model is trained from the ImageNet dataset. We also see the knowledge of the trained source model is transferred to the second target model, only using a relatively small set of training samples. The target model can be fine-tuned. By transferring the pre-trained base model to a target model, the weights from the first n layers are proven to be superior to that of pre-trained model with random weights. The further away from the first layers the data goes through, the less useful the pre-trained layers will be. Data augmentation is used to improve model performance by artificially inflating the original training data set. In this work, a rotation scheme was applied to the collected building footprints. A rotation of 72 degrees continuously to 360 degrees was applied, increasing the amount of training data 5-fold. In the pictogram here, the arrow represents an extracted building. It is rotated 72 degrees continuously into 288 degrees. You can see this increases the amount of training data 5-fold. I now want to discuss common accuracy assessment metrics that I will be used. The first being accuracy, which of course is the percentage of correctly classified buildings. Then precision, the portion of damage or no damage predictions that are correctly predicted. In other words, every point in the circle was predicted as positive. Every point in the green was correctly predicted. Precision is the measure of how many correct positive predictions over the total number of predictions. You can see that in the equation here. Next, I want to talk about recall. Sensitivity is the portion of actual positives identified correctly, and specificity is the portion of negatives identified correctly. So recall is the measure of how many positive predictions are correctly predicted. That's in the green half circle over the total number of ground truth positives, which is everything on this side. And you can see that on this equation down here. Additionally, F1 score is also calculated. Measure of the test accuracy, it's the harmonic mean of precision and recall. Then Cohen's kappa. It's a measure of how much the prediction and ground truth labels agree. And the Matthews correlation coefficient. It's a measure of the quality of a binary classification. A score of 1 represents perfect predictions, 0 represents predictions that are no better than random, and -1 represents total disagreement. Next, I want to talk about my study. I used Port-au-Prince, Haiti, after the magnitude 7.0 earthquake of January 12, 2010 as my study site. I used WorldView 2 satellite imagery with a spatial resolution of 1.84 meters taken on January 15, 2010. That's 3 days after the earthquake. I used 4 mosaic images with 3 bands each using the red, green, blue spectrum. Ground truth data was collected from products in support of the Post-Disaster Needs Assessment and Recovery Framework, produced jointly by the United Nations and the World Bank. Building footprints were extracted and manually labeled as damage or no damage. 322 training, 46 validation, and 93 testing samples were randomly generated and collected. These areas were chosen because of detailed building information was publicly available, and buildings in these areas are representative in terms of density, size, and structure. Looking at the image here, orange represents training data, red represents testing, and yellow represents validation. And I'll talk about this blue area a little bit later on. The ResNet 152 model was fine-tuned using the 322 samples first, also known as the original model. The second experiment used the augmented training samples, increasing the sample size to 1,610. Both experiments uses zero-padded training images. Here we can see a building footprint in red over the satellite image of a damaged building. The next image shows an extracted building footprint image with zero padding. Zero padding is essential because the CNN must train on images of the same size. The following images show 72-degree rotation continuously all the way to 288 degrees. The ResNet 152 models were fine-tuned with the training sets. A critical issue in machine learning is overfitting or underfitting a model. The purpose of training is to make validation loss 0. If validation loss is greater than training loss, overfitting is indicated. If validation loss is less than training loss, then underfitting is indicated. Using the early stopping technique, the model stops being trained when validation loss stops improving for 5 epochs straight. The point of early stopping is to improve model generalization and to keep the model from overfitting. The model with data augmentation stopped improving validation loss on the 15th epoch, shown here with this line. So this is the lowest validation loss. And therefore, it trained for a total of 20 epochs, shown here. The model with the original samples were trained for 6 epochs, shown here in orange. The data augmentation model is the optimal model for several reasons. training time for 1,610 samples for 20 epochs was 7.27 minutes. I did a test with 34 and 50 epochs, which gave me a test time of 12.48 and 18.37 minutes. Now this was only using 322 extracted building images rotated to make the data increase fivefold. So if the number of samples were to increase, these times would also dramatically increase. Training and validation loss were closest at 20 epochs, while also taking into consideration low validation loss. Early stopping will not only prevent overfitting, but will also allow for better generalization. A confusion matrix was constructed, shown here, to aid in the calculation of my accuracy metrics. The sum of the cell values represent the total number of data samples in here. So TP refers to true positive, there's damage. TN is true negative, FP is false positive, and FN is false negative. Positive in this case refers to the damage classification, and negative refers to no damage. Here we can see the confusion matrix result of data augmentation model. In the testing data, for example, down here, we can see that 45 damaged buildings were correctly classified and 32 no damaged buildings were also classified correctly. A total of 16 buildings were incorrectly classified. I want to look at the testing metrics, or the light blue and light orange in the graph. That would be the third bar. So the light blue and the light orange. The testing metric shows how each of the models perform overall. The testing accuracy of the data augmentation model was calculated to be 83% compared to 53% using the original training data. Recall is higher for damaged buildings when compared to no damage. The results show that 85% of damaged buildings were correctly classified using data augmentation and 60% with no data augmentation or no data rotation. Finally, looking at the Matthews correlation coefficient, we can see that the data augmentation model shows a value of 0.65, meaning the model is more perfect when compared to 0.03 for the model using original training data, which is a result no better than random. The results show that when applying data augmentation to the training samples and training the ResNet 152 model on that data, there is a remarkably improved performance compared with the model with the original training samples. Accuracy, precision, and recall are all higher between the two models, suggesting that when training a model, data augmentation on the training data, if the training sample data is limited, it is an effective way to improve model performance. Fine-tuned data augmentation model will be tested in a different area of Fort Prince for its generalization performance. I want to answer the question, how will building density and building size affect trained ResNet 152 model? To compare, the first testing set will be the same as shown previously, also known as testing A in red. Testing B is the new testing area. Testing B consists of 189 samples collected from a 7-city block area shown here. Red are damaged buildings, and blue are no damaged buildings. Testing A samples were spread out over a large area, while testing B samples were not. Testing A footprint area is larger than the average training sample footprint shown here. So the average footprint of testing A was 360 square meters, while the average footprint of training data was 291.7 square meters. Testing B's footprint is significantly smaller than both the training sample set and testing A's footprint at 197 square meters. This could have an impact on the generalization performance of the ResNet 152 model. When comparing testing A to testing B for the generalization test, we see that generalization accuracy dips to 63%. Damage recall also drops 9 percentage points when compared to testing A, while no damage recall drops 25%. Looking at the Matthews correlation coefficient, or the quality of the model, we see that that when generalization occurs, there is a MCC score of 0.30, meaning the results from the model are closer to random than they are to perfect classification model. The relatively low generalization performance of the trained ResNet 152 model can be caused by a couple of factors. One of the factors is building footprint area of the testing B compared to that of training building footprints. With damaged building footprints, there are many variations to the samples depending on the amount of damage, the type of rooftop material, and the general non-uniform nature of collapsed buildings. It is difficult to train a model to classify unseen patterns of damage with limited training samples. This leads into my conclusions and future work that I hope to develop further. This is a promising approach to classifying damaged and non-damaged buildings when a large training dataset is not feasible or laborious to collect. The training dataset can be artificially inflated while preserving labels using the described data augmentation method. The data augmentation method boosts convolutional neural network performance and prevents overfitting. Pre-trained models are highly effective in damage detection after a robust fine-tuning process. Additional automatic methods in the following tasks are necessary to improve the performance of the model, including extraction of building footprints and labeling of training data. Model generalization is also a challenge that needs to be further researched and worked on. Now, I want to thank Dr. Wong for being my advisor for 7 years for my undergraduate studies to my thesis work. I also want to thank my committee members, Dr. Kenrick Mock and Dr. Tom Ravens, for their support, feedback, and willingness to serve on my thesis committee. I also want to thank the Arctic Domain Awareness Center, in particular Executive Director Randy Key and Education and Administration Manager Elizabeth Matthews for their understanding and support. Finally, I want to thank my family, including my dad, Matthew Gores, and stepmom, Carla Gores, for the continued support of me in proofreading my thesis. I also want to thank my mom, Rebecca Meddert, and stepdad, Jeff Meddert, as well as my siblings, Kyle and Skylar Gores. Finally, I would also like to thank my grandmother, Melissa Gores, all for their support. And with that, I'm happy to answer any questions that you may have. Thank you.
Oh, thank you, Tristan. That's a great presentation. Is there any questions from the audience or committee members?
I have a question.
Yes.
Tristan,
Hello.
in your view, would it be helpful to sort of collect high resolution imagery of all major cities in earthquake prone areas sort of in advance and have them sort of readily available for this type of analysis, or is that not necessary?
Yeah, I think that I've had that same thought. I think that would be very useful, especially when training models. For example, a city like Port-au-Prince may have a different type of infrastructure when looking at a satellite view than someplace like New Orleans or Anchorage, using like most notably different colors or different building materials may affect classification. I think one challenge is keeping up consistent and useful building footprints that are co-registered with imagery that can be used in classification and training. Extracting building footprints is one of the primary challenges of this work.
Thank you.
Can you say a little bit about kind of how you came up with the process, like how you came up with the design for your experiment? Like how did you end up with using, ResNet 152 as opposed to 101 or 50? Like how you came up with the um, with the scheme to rotate with 5 intervals. So kind of the process you came up with for the whole experimental design.
Sure. It was an evolution in my thought process. Originally, I was using the ResNet 34 model to, number one, because it was available within the ArcGIS deep learning library. There were other models in there, and I was testing a few of them. I was testing a number of the ResNet models, and I found that the ResNet 152 worked, I think, the best for me. And what was the second part of your question?
Like on the data augmentation, so you ended up with 72 degrees. Like,
Yes.
why not 30 degrees? Or I suppose you might do better if you do more
Yes.
rotation.
Actually, I actually tested multiple degree rotation. I decided on 72 degrees. I tried 90 degrees, which would increase the data fourfold. 72 would increase fivefold. I noticed that I had better accuracy when I increased the amount of training data. And I did rotation to the training data because the challenge of collecting building footprints in Haiti, the available data in Haiti for building footprints is not as good as I had hoped. It's kind of poorly co-registered to the imagery that I have, and in some places the building footprints do not match, or they're sparsely spread out, and they don't match the building rooftops that I'm seeing. So it was an evolution of my thinking to, hey, why don't we rotate the training data to see if we can get artificially inflate the amount of training data. And I think this would be useful in a limited time frame situation when collecting after a natural disaster, because you want to get information out to emergency response personnel as soon as possible.
Are there other kinds of transformations that might be useful for augmenting the training set?
Yes, I did rotation, but I think there are also other options that could have been done, such as flipping or mirroring a model, or excuse me, an image. Also, there have been many studies on using many different resolutions of imagery to look at buildings, from maybe perhaps a 5-meter resolution to a 2-meter to a 1-meter or 30-centimeter resolution imagery. And there have been a number of studies that use multiple resolutions of imagery to classify these buildings.
Okay, thanks.
No problem.
Tristan, just following up on Kenrick's question, is the idea of rotating the images, is that something you came up with on your own, or is that something you had seen elsewhere?
It's hard to say. I don't recall. No, that wasn't an option in the ArcGIS learning library, but I've seen other studies use some sort of a data augmentation technique to inflate their amount of training data. So, it was kind of a little bit of both.
Well, in my view, this work is definitely publishable, and so my hat's off to you. A lot of times, at the end of a thesis, in principle, they all should be publishable, but sometimes they're not quite publishable. But I would say, being relatively ignorant in this area, I would still say that it's definitely publishable. I'm kind of curious if Keisha agrees with that.
Yes. So Tom, I think Tristan did a very thorough, I think, comparison regarding those experiments. I think definitely valuable to publish the findings. Even though without further experiment, I think currently with the current findings and the writings he had from the thesis, I think it's worth to explore the place to publish.
Yeah, unfortunately, the ISIP, the conference happening here in Anchorage this fall, the deadline has passed, but I'm sure there are other.
Oh.
Another question. So you had 322 training samples. It sounds like that was like a static training set. Did you think about some kind of cross-validation? I know your generalization study kind of gets at that, but if you had thought about doing a cross-validation kind of study?
No, that I did not think about doing.
Okay. Can you say a little bit about like your implementation? So I think you had written you used Jupyter Notebook, but you also like kind of how you actually implemented the whole thing.
Sure. I use ArcGIS Pro. I mosaicked 4 Walter 2 satellite images together, and I extracted. They were already orthorectified, and I manually selected building footprints. And I used a PDF that I got from the United Nations, which showed it was pixelated, but I kind of like georeferenced that over my image, and they had like pixels for red indicating damaged building, black for no damage. So I went to the red pixels and I saw that there was a damaged building there. So I used the United Nations data as well as my own common sense to extract a building footprint using satellite images that were taken about like 3 days prior to the earthquake as kind of a reference building footprint. So I extracted those manually. I had a large file of those, and then I went to Jupyter Notebooks and I used scikit-learn's training and testing data splitting tool to split my data into 3 different data sets. I think from the top of my head, I used 70 training, 10 validation, and 20% testing. And then I used ArcGIS deep learning library to train, validate, and test the model, while also creating shape files which were uploaded into ArcGIS Online. I still have those too.
Okay, thank you.
All right, is there any other questions? I think I already asked questions before this defense, so I think I'm okay with now. Is there any other questions from the audience or comments? All right, great. Thank you so much, Tristan. Sorry.
I just want to congratulate you, Keisha, on your first graduate student. Is that correct?
Yes, yay.
Yeah, no, it came out really, really well. So, I'm totally impressed with the kind of work you guys do in geomatics. So, because I really didn't understand your department so well, but now I think I understand it a lot better. With it, this is very high level analysis. So, very good work.
Thank you.
Thank you. I think Tristan is also our, I think, excellent student. After I think we got this great chance for him to continue as a master degree, so I can keep him longer. So yeah. I think I'm very proud of him.
Yeah, I was giving my Geomatics capstone presentation to the advisory board. Then immediately after, Kaisha just offered me like master's degree position here. So I took it up within like 5 minutes. So.
Well, Tristan, I think it's just you need to know that Tom actually is helping on that process too. He's he actually supporting from the ADAC Center research aspect to support you to join that support. So
Thank you.
all right. If there's no questions, I appreciate everyone from the audience, as well as the family members from Tristan to join our important day for this Thesis process. So I think up to this stage now, I would like to have a private meeting for all the committees regarding the approval or questions regarding the Tristan's thesis. And then I'll ask Tristan, to join back to this Zoom meeting after 5 minutes, so that we'll inform you the decisions from the committee. Okay. Thank you. Do you have any last comment to the audience and to us, Tristan?
I just want to again thank everyone here for supporting me and throughout my educational career here. All right, so I'll leave and
okay.
Come
I'll
back.
see you 5 minutes a little bit.
I'll come back at 3:55.
Sounds good. I think we still have 2 members here. Kala, is it Kala? Is that right pronunciation? Could you please give us some private meeting so that, or is there any way that we can do private meeting here?
Or I think you might be able to kick him out.
Break out the room, right? Okay. Yeah, I forgot that. Okay. Let's see. Assign manually. And me. All right. Then can I just start? All right. So Kenrick, Tom, are you get the invite? Oh, we're still recording. I'm gonna stop.